Hello everyone, this is Abhishek Mahanti and welcome to lecture number 19 of the chapter Electric Charge and Field. Students, in this lecture, we'll discuss about a very small topic, and the topic name is oscillation of an electric dipole in a uniform electric field. So, let's get started. So students, we already know that two equal and opposite charges separated by a small distance forms a dipole, and when the dipole is placed inside an electric field, it experiences a torque, and we have derived the expression for the torque. Tau is equal to Pe sin theta, where P is the dipole moment of the electric dipole, E is the electric field strength, and theta is the angle between the dipole moment and electric field. And we had also discussed that if theta equal to 0, means if the angle between dipole moment and the electric field is 0, then this position is known as the position of stable equilibrium position. And if theta is equal to 180 degree, means the dipole moment is opposite to the electric field, then that position is known as unstable equilibrium position. And under these two positions, the torque acting on the dipole is 0, and theta equal to 0 is known as the stable equilibrium position, theta equal to 180 degree known as unstable equilibrium position. So the topic name is oscillation of an electric dipole in a uniform electric field. So first we must understand why should a dipole oscillate in a uniform electric field. So look at the diagram here. We have a uniform electric field which is represented by the parallel and equispaced field lines, and suppose E is the strength of the electric field. Inside this uniform electric field, we have an electric dipole consisting of two charges, minus q and plus q, and the separation between the two charges is 2a. So the dipole moment will be how much? P is equal to q into 2a. This is the dipole moment. And now the dipole is in the stable equilibrium position, because if you look at the diagram here, the dipole moment is parallel to electric field. We know that the dipole moment is directed from negative charge to the positive charge. So here the dipole moment P vector is parallel to E vector, and it is in the stable equilibrium position. So the torque is 0. Now if I slightly disturb this position of the dipole, then what will happen? For example, suppose I will rotate this dipole about its center through a very small angle theta. Suppose I will rotate the dipole about its center through a very small angle theta in the anti-clockwise direction. So I have rotated through a very small angle theta in the anti-clockwise direction. Now a torque will act on the dipole. So the torque is equal to how much? Pe sin theta, where theta is the angle between V vector and E vector. And look at the situation here. I have rotated the dipole in the anti-clockwise direction, means the angular displacement is directed outward, because we know that for anti-clockwise rotation the angular displacement is outward, and for clockwise rotation the angular displacement is inward. So since I have rotated the dipole through a small angle theta in the anti-clockwise direction, so the angular displacement will be outward. And now a torque will act on the dipole, and the tendency of the torque will be to take the dipole back to its equilibrium position. Means the torque will again rotate the dipole in the clockwise direction, and we know that if the torque rotates a body in the clockwise direction, means the torque is inward. So here the torque acting on the dipole will be inward. Similarly, if you rotate the dipole in the clockwise direction, then the torque will rotate the dipole in the anti-clockwise direction. Means the angular displacement theta and the torque tau are opposite in direction to each other. So tau is equal to minus of p sin theta considering the direction. Tau is equal to minus pe sin theta. The negative sign indicates that the torque and the angular displacement are opposite in direction. And since I have taken the theta, the angle to be very small, so for small angle, sin theta is nearly equal to theta. Since I have rotated the dipole through a very small angle, so the restoring torque is equal to minus pe theta. In place of sin theta, I can write theta. This torque is known as restoring torque because this torque helps the dipole to take it back to the initial position. Is that clear? So the restoring torque is equal to how much? It is minus pe theta. Due to this restoring torque, the dipole rotates in the clockwise direction. But when it reaches at this position, it does not come to rest because it has some inertia, and due to its moment of inertia, it also overcomes this position and it goes in this direction. Again, another torque acts on it which rotates the dipole in the anticlockwise direction. So in this way, what happens? The dipole oscillates about the equilibrium position. The dipole oscillates about the equilibrium position like this. This is minus q, this is plus q. So this is the equilibrium position of dipole. But if I rotate it in anticlockwise direction, then the torque will take it back in the clockwise direction, and once it reaches at its stable equilibrium position, it does not come to rest because it has some inertia. So it overcomes this position and it goes in the clockwise direction, and again the torque take it in the anti-clockwise direction. So in this way, what happens? It oscillates, the dipole oscillates about its equilibrium position, and we have to find what is the time period of that oscillation. So for the small angle theta, sin theta is equal to theta, the torque tau is equal to minus p theta. And in class 11 we had discussed that the torque is nothing but I into alpha, where I is the moment of inertia and alpha is the angular acceleration. So I alpha is equal to minus pe theta. This dipole has some angular acceleration. The expression for alpha is d square theta by dt square, the second derivative of angular displacement. So I into d square theta by dt square is equal to minus pe theta. That implies d square theta by dt square is equal to minus pe divided by I into theta. Is that clear? That implies d square theta by dt square plus pe by I into theta is equal to 0. This equation resembles to the differential equation of angular SHM. We know that the differential equation of angular SHM is d square theta by dt square plus omega square theta is equal to 0. So if you compare these two equations, this is equation 1, this is equation 2. If you compare these two equations, you can say that omega square is equal to pe by I. Omega square equal to pe by I. That implies omega is equal to square root of pe by I. Omega equal to square root of pe by I. And what is time period? Time period is t equal to 2 pi by omega, that is equal to 2 pi divided by pe by I square root, that equal to 2 pi I by pe square root. So this is the expression for the time period of oscillation of the electric dipole inside the uniform electric field. Hopefully you have understood the derivation. So this is the very small topic, and this topic is not in your syllabus, but you have to know about this topic. So I hope that all of you have understood, and in the next class we'll come with some new concept or some new numericals. So till then, have a nice day and bye bye.